Hello and welcome to Amy's whistle-stop tour through things I adore. Moles were the bane of my life at the start of A-level chemistry and also at GCSE. I really didn't understand them at all. I hated them. They had this kind of cute sounding name, but that didn't change the fact that they were evil things and I just didn't get it at all. So I worked hard at moles. I really did dedicate so much time to get my head around them. And here we are, a video on moles, which I never thought I'd be making. I'll explain it quite simply because that's what I needed. So we'll be covering moles, concentration, molar mass, volume, and hopefully you'll have mastered it by the end. So chemistry very often involves reactions, combustion, decomposition, neutralization, precipitation, synthesis, displacement, the list goes on. But how do we know how much substance we've formed and how much we've used? Well, we can weigh it and measure the mass. We can use a gas cylinder to measure the volume. But grams and decimeters cubed don't tell us how many particles have actually reacted. We want to know this because reactions occur on an atomic scale. Introducing the mole. Moles are basically a unit of measurement representing a fixed number of particles. So we can use this fixed number of particles to work out how many particles we have of any substance. So you might be wondering, what is this fixed number of particles you keep going on about? Well, 1 mole contains 6.02 times 10 to the power of 23 particles. So 1 mole of carbon atoms contains 6.02 times 10 to the 23 carbon atoms. 1 mole of calcium contains 6.02 times 10 to the 23 calcium atoms. 1 mole of carbon dioxide contains 6.02 times 10 to the power of 23 molecules of carbon dioxide. This huge number is known as the Avogadro constant, and this is Avogadro on the screen, although he didn't come up with a constant. I think it's just named after him. You might be thinking, why on earth 6.02 times 10 to the power of 23 particles? That's so many, and such a random number of particles to choose. Well, firstly, atoms are tiny. The word atomos literally means uncuttable, and although we can cut and analyse them further into protons, neutrons and electrons, atoms are the smallest unit of matter that can be identified as deriving from a set element. So if we look at any atom of carbon-12, it has 6 protons and 6 neutrons. Atoms are minuscule, but it is important to know how many atoms are reacting, so we do have to deal with these huge numbers somehow. Next, we can look at whether this number is random, and it's not random. It's not just pulled from thin air. 6.02 times 10 to the power of 23 is the number of atoms in 12 grams of carbon-12. So if you had 12 grams of pure carbon, you'd have exactly 1 mole of carbon atoms. 6.02 times 10 to the power of 23 atoms. That is huge. It could sell out Wembley Stadium trillions of times if each atom had a little seat. And just as it isn't practical to measure a 10k race in centimetres, it also isn't practical to measure a chemical reaction in individual atoms because you'd end up with such huge numbers. So the amount of substance in moles is used, knowing that a mole represents that fixed number of particles. So a mole is a unit of measurement. If you run a kilometre, you run a set distance. It is 1,000 metres. It is 100,000 centimetres. It isn't practical to measure it in centimetres when you can say 1 kilometre. The metre is a base measurement with which we compare different distances. In the Olympics, the track is 400 metres. If we didn't have a way to measure distance, then these Olympic runners would not, they wouldn't know what distance they were running, and they wouldn't be able to work out the speeds they went or how they placed against their competitors. Moles are also just a quantity of particles, which come in very handy for chemists. So, here is carbon-12. It is the 6th element on the periodic table. See, it says 12. The 12 is the relative atomic mass. So relative to the other elements, carbon has a mass of 12. Hydrogen has a relative atomic mass of 1. Compared to carbon, it has 1/12 of the mass. Chlorine has a relative atomic mass of 35.5. So that's pretty much 3 times the mass of carbon. So atoms all weigh different amounts, and we can use relative atomic mass as a kind of ratio. They have different weights because all atoms have different numbers of protons, and often neutrons too. An atom's relative atomic mass is the sum of its protons and neutrons, which both weigh 1 unit. So carbon has 6 neutrons and 6 protons, as you can see in the diagram at the top right. So it has a relative atomic mass of 12. Hydrogen atoms have 1 proton and no neutrons, so it has a relative atomic mass of 1. And chlorine has 17 protons and exists in various different states with different numbers of neutrons. The relative atomic mass is 35.5. Deduct the proton number 17 and we can see an average number of neutrons of 18.5. So if protons and neutrons give rise to the relative atomic mass, and carbon has a relative atomic mass of 12, then maybe we can see why it was decided that 1 mole should be the number of particles in 12 grams of carbon-12. Because if 12 grams of carbon contains 6.02 times 10 to the power of 23 particles, and hydrogen is 1/12 of the mass of carbon, then 1 mole of hydrogen will have 1/12 of the mass of carbon. And 12 divided by 12 is 1 gram, so 1 mole of hydrogen has a mass of 1 gram. And look, the relative atomic mass of hydrogen is 1. So if you add a gram symbol to the relative atomic mass, then you know the mass of 1 mole of that element. Okay, take chlorine. Well, as we know that a mole of carbon atoms has a mass of 12 grams, and we know that a chlorine atom is approximately 3 times heavier than carbon. Well, if 1 mole of carbon weighs 12 grams, then 1 mole of chlorine atoms will weigh 2.95 times this, which is 35.5 grams. Or just add a gram sign to the relative atomic mass. So basically, the relative atomic mass is a ratio, and you can use it to find out how heavy an atom of a different element is compared to an atom of carbon, and therefore how heavy a mole of atoms of that element is compared to a mole of carbon atoms. Sorry, that was quite a long explanation. I could have just said a mole is a unit of measuring the amount of a substance and left it there, but I think it's important to know why they're so useful. Now, as you know, 12 grams of carbon is 1 mole. What if I had 75 grams of carbon? How many moles would that be? Well, you just divide it by the atomic mass. 75 divided by 12 is 6.25 moles of carbon. My teacher used to tell me moles equals grams over rams, meaning moles equals grams divided by the relative atomic masses, rams, and it just stuck with me. So that's what I use to work out the amount of moles given the grams and the relative atomic mass. So what about 24 grams of sodium? How many moles is that? So if you divide it by the relative atomic mass of sodium, 23, then you get 1.04 moles. Okay, what if I had 5 grams of carbon dioxide? Oh dear, it looks like you have more than one element. But it's simple, you just add up the relative atomic masses. So 12 for carbon and 2 lots of 16 for oxygen is 44. And then you do exactly as you would have done. So divide the grams by the relative atomic mass. And that is 0.11 moles of carbon dioxide molecules. The same with CH4, methane. Add up the relative atomic masses. So 12 plus 4 times 1 is 16. And then divide 24 by 16 to get 1.5 moles. So the number of moles equals the grams divided by the atomic mass if there's just one element, or the relative molecular mass if there's more than one element, and that's just the sum of the relative atomic masses. So with this in mind, you can also work out grams and molecular mass from moles. So say Roberta has 14 moles of sodium. Now sodium has a molecular mass of 23. So find the mass in grams. So moles equals grams over mR, and that will rearrange to moles times mR equals grams. 14 times 23 equals 322 grams. And there you have it. What about this one? Boris has 12 moles of potassium bromide, and that has an MR of 39.1 plus 79.9, which is 119. So find the mass. Now, 12 times 119 equals 1,428, and that is the number of grams. So then, finally, you can work out the relative molecular mass if you've got the other two, the moles and the grams. So this is the sum of the atomic masses in a compound or molecule, and if you've just got one element, then it's just the atomic mass. So, I have 5 moles of an unknown element with a mass of 121.5 grams. What is the MR? And what is the element? So, first we must rearrange the equation. Grams divided by moles equals MR. And 121.5 divided by 5 equals 24.3. And then look at the periodic table and you'll find 24.3 as an MR equates to magnesium. Yay! Now here's a harder one. I have 363 grams of a 3 mole solution of XCl, X being the unknown. So what is it? So grams over moles equals the MR. So 363 divided by 3 equals 121 as the MR. So the AR of Cl of chlorine is 35.5. Deduct that from 121, leaving 85.5, which is the AR, the relative atomic mass of what? Oh, rubidium. So I think I'm going to leave it there. I was going to talk about concentration and volume, but you know what? I think we've done enough. So yeah, that's it for my video on moles. I